Okay, so solubility, KSP. We're going to be talking about solubility equilibria and the solubility product. Now, the title is not why do we add fluoride to drinking water, but we're going to use this as an example of what KSP is, what solubility equilibria are, and why is it important. So first thing, solubility equilibria describes how solids can or cannot dissolve in solution. So let's take a look. Oh my goodness, gross. So before there was fluoride, well, I don't know what people did before there was fluoride, but before there was fluoride, you would get little gritty bits in your teeth, and then bacteria would grow on whatever food was stuck between your bits in your teeth. Gross, right? What should you do? Well, let's see. So we're going to get rid of the hydroxyapatite by replacing the hydroxyl group with fluoride. I'm hoping that you read this earlier when I was talking. We form fluoroapatite and calcium fluoride on your tooth enamel. This helps your tooth enamel because it will no longer be as susceptible to acid degradation. Why does that work? What does chemistry have to do with this? So let's talk about KSP. The solubility product constant is just a fancy name for the equilibrium constant of reactions for dissolving insoluble ionic solids in water. So an example is calcium fluoride is not super soluble. It can break down into calcium ions and fluoride ions. This right here is the reaction for the KSP. SP just stands for solubility product. The KSP for calcium fluoride. The solid that we're talking about is always the reactant, and the ions formed are products. You just look at the chemical formula here to figure out what the coefficients are for the ions. Now this KSP here is just a fancy equilibrium constant. We've been learning about equilibrium constants. You should know K is just products over reactants. So products, calcium 2 plus concentration times the F minus concentration squared, because we square if we have a coefficient of 2. So this is just a regular old K. Now you might be wondering, why don't I have the Ca? Oops, oh my goodness. Okay, so now we have a little special Westridge event going on that everyone knows about. Liberty and North Korea Club is having a free documentary. Okay, back to chemistry. So where were we? Let's see, we're talking about the KSP. Oh, I was asking, why don't I have CaF2 in the denominator? Because normally the K's are products over reactants. Why is the CaF2 not showing up here? Because it's that's right, it's a solid. Okay, we don't have solids in the case. Okay, and this is just giving you why we use the term SP, solubility product. Multiplication means product. Also, these are products. So, solubility product. Okay. So let's do some problems. So you might be given the KSP, or you might be given the solubility. So there are two types of problems. This is one of the classes where you're given the solubility and you're asked to find the KSP. So you always need to write a reaction. We're in chemistry, we write reactions. So we're talking about this particular compound, and it's going to break into its ion. So try to think about, what are you going to produce? You could write this reaction yourself following this symbol. We'll have this as a solid on the left. How many Bi's will we have? 2. How many S's will we have? 3. And the charge of the Bi, you always have to include your charges in the products because these are always forming ions. And hopefully you figure out what the charges should be. +3 for the bismuth, -2 for the sulfide. Bismuth 3 and sulfide. Okay. So now the solubility is how much can dissolve per liter of solution. And when we say how much, we're talking about moles, the molar solubility. If you're given how many grams can dissolve per liter, just convert that into moles per liter using the molar mass. Okay, so notice if 1 times 10 to the negative 15th molar of the Bi2S3 can dissolve, then we just use stoichiometry. There's a 2 in front of the bismuth, so the solubility times 2 will be how much bismuth can dissolve. And for the sulfide, we would multiply the solubility by 3 because of this coefficient. There's always a 1 in front of the solid, so we're just doing stoichiometry to convert each ion, to convert to the solubility, what would dissolve for each ion, how much would dissolve. So notice the sulfide has a 3 times the solubility because there's a 3 here. And the definition of the K would be bismuth 3 squared times sulfide cubed. So we just take these numbers here, right here, we plug them in. I plug them in, and we put that in our calculator, and my goodness, that is a tiny KSP. Very, very tiny. So I had mentioned there are 2 types of problems, one in which you're given the solubility. That's the kind we did, right? Oops. Sorry about that. One in which you're given the solubility and asked to find the KSP. And in that case, you just look at the coefficients for each product and identify the concentration based on stoichiometry and plug into your KSP, your K expression. Those are pretty straightforward. So given solubility, use the coefficients to get stoichiometry, plug into your expression, and you can find your KSP. The next problem type, hang on, is down here. I'll explain what you see up here in a moment. The other kind of problem is you're asked to find the solubility given the KSP. In that type of a problem, you're going to do an icebox. Now, just real quick, this is on your notes already. It's just a chart of KSPs for many, many, many different substances. We will be using this chart in class at different times. So this is just for your information. By the way, if the stoichiometry is the same, so when I say that, I mean you make the same number of positive ions and the same number of negative ions for 2 different substances, you can identify which substance will be more soluble just looking at the Ks. But you have to have the same stoichiometry. So, for instance, I could compare the solubility of these 2 things because each of these produces 1 Ba2 plus and 1 of the negative ions, 1 carbonate, 1 that is chromate. So now I can compare the KSPs. This is a bigger KSP. This is a smaller KSP. Let's look back here. Now, the definition for the KSP is the products, the ions are on the right side. So if you have a bigger KSP, a bigger K means you go farther to the right. Remember, the bigger the K, the more products you make. If you can make more products, that means more of you can dissolve because you're making more of this. So the bigger the K, the more soluble the substance is. You might want to write that down because that's not listed in the notes anywhere. So make a little note for yourself. Bigger K means more soluble if, and only if, you have the same number of positive and negative ions. So the question is, could I compare these 2 things? The answer is no, I cannot, because BaF2 breaks into 1 positive ion and 2 F minuses, not 1 F minus. So I cannot compare these 2. I'd have to do an actual calculation to find the solubility. Okay, back to the second kind of problem. So given the KSP, find the solubility. This is the second class of problems. And in that case, you need an icebox. So first you write the reaction. Copper 2 means you have copper 2 plus. Iodate is IO31 minus. You don't have to memorize that. That would be on your polyatomic ion sheet. So the formula for that, you should try to write the formula right down. You can pause this, but I'm about to show it. So pause if you want to write that yourself. Ah, there it is. Okay. So solid copper 2 iodate makes 1 copper 2 plus and 2 iodates. Just a stoichiometry. Remember when you go from a formula, from a name to a formula, you have to make sure that the charges add up to 0. That's why we need 2 iodates for every 1 copper, because we have a copper 2, and iodate has a -1 charge. Okay, so here's our reaction. You'll have to remember how to do that. You will have your polyatomic ion sheets for problems. We set up an icebox. Okay. Now, remember, solids we ignore. And if we're checking for the solubility, we're saying we start with none of this. The change row, how much will form? The coefficient is 1, so we have just 1x. The coefficient is 2, so we have 2x. Oh, good. I have an arrow. Nope. I was hoping to have just an arrow. We'll see if that works. Okay. So coefficient of 1, nope, we have 1x. Coefficient of 2, we have 2x. This reaction is going to the right if we're going to form ions. When we're talking about how soluble something is, we're saying how much of the ion can we form? How much of this will dissolve to form those ions? So this reaction would be going to the right, especially since we're starting with none of the ions. Okay, and for the next row, the E row, we just add the first 2 columns, and again, we are ignoring the solid. Now, in all these problems, x will be our solubility because this has a coefficient of 1. And anything that has a coefficient of 1 would just be 1x. So if this were not blank, if this were an actual chemical, we would just have an x here. And this will be the solubility because it's a 1-to-1 ratio. If we find something, how much of this copper 2 will dissolve, and we were to use stoichiometry, we could convert from copper 2 to copper 2 iodate. All right, so now the KSP expression. Let's see, I'm going to cover this up a little bit. Isn't quite working the way I wanted to, but that's okay. All right, KSP expression you just get from looking at the reaction. So the KSP would be copper 2 plus times IO31 minus squared by the definition. You should always write down your KSP definition. And then as we plug in, we'll plug in the values from the E row. Okay, so I just plugged in those values. And now I was given the KSP right here. So I know that this is equal to 1.4 times 10 to the minus 7. And now I can solve for x because the left side is equal to 4x cubed. Don't forget to square the whole thing. So we have 4x squared times x is 4x cubed equals a KSP. Solving for x. There we go. We have x. So I'm explaining again why x is the solubility of copper 2 iodate. Notice you can just use stoichiometry. I can also calculate, if asked, I could find out what's the copper 2 concentration, what's the iodate concentration. The iodate concentration would be 2x. The copper 2 concentration would be x. Okay, but this particular question only asked for the solubility. So all I need to report is x. And there you have it. Okay, so there were the 2 classes of problems I explained. Given KSP, find the molar solubility. Given the molar solubility, find KSP. Another class of problems is called the common ion effect. So we add a soluble compound to a solution with an insoluble compound, I can't speak, that has a common ion. When you do this, the insoluble compound becomes much, much less soluble. We use this for cleaning up polluted water. If we have something polluted with, say, lead, and we want to precipitate out the lead, I could add something that will precipitate out the lead, which will make the lead ions completely insoluble. All right, so here we go. We're going to do a copper 2 example. So you've got a lot of water contaminated with copper 2 ions. I want to get rid of all the copper. I could use iodate, and the copper would precipitate as copper 2 iodate. Now, I'm going to add sodium iodate, and I'll be able to precipitate out much more of the copper. So let's watch. The sodium ion is just a spectator ion. So we're going to find out what the solubility of copper 2 iodate is in a 1 molar solution of sodium iodate. I want to point out that in this last example, we just found the solubility of copper 2 iodate here. It's about 10 to the negative 3 molar, so 0.003 molar. You're going to find it goes way down. Okay. We still have the same reaction we had before with the copper 2 iodate. When we say we add sodium iodate, 1 molar sodium iodate, we don't put sodium iodate as the reaction here. The sodium, you have to identify that as a spectator ion. Remember, our alkali metals are usually spectator ions. The key is, if I have 1 molar sodium iodate, I have 1 molar iodate. So now my initial concentrations are different. The iodate initial concentration is 1 molar. One common mistake is students will look at the coefficient here and think they're supposed to do something with that coefficient in this I row. You ignore the coefficients here. What is going on is you're just finding your initial concentration of iodate, which you get right here from this 1 molar solution of sodium iodate. Then we do the problem just as we did before, and you will notice, so we fill in our E row using the coefficients. Sorry, we fill in our change row, how much will form using our coefficients. Why did I leave this empty? Because copper 2 iodate is a solid. That's right, it's a solid. Okay, for the E row, equilibrium, we add the initial and how much it changed by, how much the initial changed by. We add these two rows together to get our E row. Now, here's that. We're adding something to a number. Now, we know that K is really tiny. We were given K in this problem here, 1.4 times 10 to the negative 7. This number is much smaller than 1, so we can make the assumption that X is much smaller than 1 because K is much less than 1. So this 2x is going to be, we actually would assume that 2x is much less than 1. There we have it. So we're going to assume 1 plus 2x is approximately just 1 because the 2x is so small. Now we plug into our KSP expression, which, okay, hang on. The KSP expression, you always want to write that out. Ignore what's down here for now. You write out your KSP expression, you plug in the numbers that we have right here, and we get X for the copper to the first power because of the coefficient, and then the iodate concentration, we look in the E row, iodate squared because we square based on the definition of K, and then that equals KSP, and solve for X. So we get X is 1.4 times 10 to the 7th molar. Now that's the new solubility. Notice when we didn't have sodium iodate, the solubility was 3 times 10 to the negative 3 molar. But now look at this. Our solubility is 1 times 10 to the negative 7 molar. Remember X, when you solve for X, that is your molar solubility. Okay, a 10,000-fold decrease just because we added sodium iodate. So that will definitely get the copper out of solution. Okay, you're going to try a few problems on your own. So you should try to work through this. I'm going to show you the solution in a moment, but you want to pause this, try to do this on your own, and now I'm going to show you the solution because you've paused it, right? You know you've paused this, tried it on your own, and here's the solution. Okay. So another problem. Notice these are asking for the KSP. This is the kind where it's okay. We're having students walking in the classroom. They know, oh my goodness, lots of students walking in. That's all right. You can all say hi. I'm recording. Oh my gosh, you're on here.
This is Maya Blumenthal. Please include me.
Okay, back to the recording. Where are we? I'm so confused now, Maya.
I feel like I'm the lovers.
You are. You'll be on here forever. Assuming I don't change the video at some point. Okay, so here's another problem. Go ahead and pause it. Did you want to come and say hi too?
Sure.
No, but
Oh, look.
Hi,
there
I'm
they are.
Helena. This is Frances. Yeah. Love
Okay.
chemistry.
Oh, Helena, you just put that on my video.
Oh, I'm just kidding. I love this class.
Okay. All right, so you should pause the video right now and try this problem on your own. It's okay. You can talk if you want to. You could be forever on one of the videos. Try this on your own. Pause the video. And I'm about to show the solution. So if you want to do it on your own, make sure you pause the video. And here is your solution. Okay, now next kind of problem. This is you're given the KSP. That means you need to use an icebox. So pause the video. Try this on your own. The example is given at the bottom of page 2. You can just follow that example, and here's the solution. And there we go. Oops. There you go. There's your answer. Okay. And now time for some chemistry humor.
think like a proton, always positive. What is the chemical formula of a banana? BaNa2.
And that's our chemistry jokes for the day.